everything in the title throughout the talk. But just for an outline of what I'm going to be discussing today, we're just going to set up a random matrix model, discuss some previous results relating the model to free probability. Then we'll look at my work with Sean that gives us, the title of the talk. And then I want to end, because this is a summer school, with some free probabilistic questions that I came into this school hoping to gain more insight into. Look once, right? Okay. So throughout, we're going to be discussing the empirical spectral measure. We've seen this a few times now. You just put a Dirac mass at every eigenvalue and then scale to keep this a probability measure. So if Xn is a random matrix, this is going to be a random measure. And then, a lot of results in random matrix theory are for certain models of Xn showing that this measure converges to a deterministic limit. So the matrices we're going to be looking at today are going to be of the form ln equal to some an minus dn. So here an is going to be a n by n random real symmetric matrix, and dn is a diagonal matrix where the ith diagonal entry is given by the sum over the ith row of A. Okay, so we're going to require that A is real symmetric and not complex remission, because we want the entries of D to be real so that everything stays symmetric. So in the random matrix literature, these are referred to as random Laplacian or random Markov matrices, kind of depending on what your motivation is. So if you're thinking of AN as the adjacency matrix of a graph, then this is the negative of the combinatorial Laplacian of the graph. The sign convention, it's easy to tell how that affects the spectrum, so it doesn't matter. And then if you just think of AN as having positive entries, not necessarily 0, 0, 1, or maybe non-negative entries, then this is going to be, the ln is going to be the infinitesimal generator of a Markov process, which is where the name Markov matrix comes from. So we're going to be using Laplacian, but I guess we're using the sign notation of a Markov matrix. Any questions about the model before I continue? Okay. So how are these related to free probability? So an and dn are definitely not independent, but if we kind of imagine for nice an that they act sort of asymptotically free, although I'm not going to discuss any results about that, but maybe they're kind of close to independent for large n, then free probability would give us a guess that the limiting spectral measure of ln might just be the free convolution of the two respective limits. Okay. And it turns out that this is the case for Wigner matrices. So this is a result of Breek, Dembo, and Zheng from 2006, that if an is a Wigner matrix, so independent identically distributed entries of symmetry of mean 0 and variance 1, then with probability 1, the empirical spectral measure of ln over square root of n converges weakly to the free convolution of the semicircle and the Gaussian, which I'm going to denote as SC, free additive convolution G, throughout the talk. So it should be, AN is of course going to a semicircle. That's Wigner's famous semicircle result. So why is the diagonal approaching a Gaussian? Well, if you look at these diagonal entries, they're just going to be the sum of mean 0 unit variance random variables. And then we're scaling by square root of n. So every diagonal entry is looking more and more like a Gaussian. Two diagonal entries only share one entry of A. So their covariance is going to be 1 over n after scaling. So for large n, D just looks like a diagonal matrix of independent Gaussians. The law of large numbers tells us that its empirical spectral measure should be going to a Gaussian. That's not really hard to show. So I think this is great. You're studying random matrices. How could you ask for a better measure than the free convolution of the semicircle and the Gaussian? They're the two best measures. And so we're going to be looking at sort of these Laplacian models, but now they're going to be sparse. So what I mean by that is the entries are still going to be IID up to symmetry, but now they're going to be of the form epsilon ij times xij, where the xij are independent standard Bernoullis, up to symmetry. And the epsilon ij's, the xij's are independent standard Gaussians up to symmetry. And the epsilon ij's are Bernoullis, where the probability of being 1 is some Pn going to 0 as n goes to infinity. So what we're thinking is we're just taking, I guess, a GOE matrix, and we're deleting entries. We look at a particular entry and we flip a coin If it's heads with probability Pn, we keep it. If it's tails, we delete it. And then we're deleting a single entry with higher and higher probability. So there are kind of two regimes you can look at in these sparse models, or really there's a lot. But the first is that if NPN goes to infinity, then it's known that the empirical spectral measure of ln over square root of NPN converges still to this free convolution. So this is a result of Zhang from 2012 for adjacency matrices, after centering and rescaling. And then I'm studying Chatterjee and Hazra, from last year for the more general case. So just mean zero variance 1 entries before you set them equal to 0. And they don't state this explicitly. I couldn't find anyone who stated the general case explicitly, so I just went through every Laplacian paper I knew, and this is the most recent one where you can check that their conditions apply to this sparse model. So I really hope I'm not leaving anyone else. Different variants. So they use generalized Wigner matrices, right? So if in their model, they call them AN, like their entries are AN, right? If you set if you set Aij to be Xij over square root of Pn, this would apply to their model and their conditions hold. Like the two of them, the graph-on condition is easy, and then the moment is easy. The only hard one is sort of the Lindenberg condition, but even then, that's just like it's just, you got to work it out, but it's pretty straightforward. But yeah, so even again, this paper is more about a graph-on approach to these Laplacians, but it was the first one I could find that handled the general case. But if it works for adjacency matrices, it probably works for the general case. Okay. So this phenomenon kind of happens a lot in random matrix theory, where if NP is going to infinity either at all or sufficiently quickly, like faster than some powers of log like we saw earlier, then you usually just recover the non-sparse result. So we're not going to be looking at that case today. We're going to be focusing on NP going to some constant in 0 to infinity. So in this situation, the empirical spectral measures still converge, so for AN and DN, but not to a semicircle nor a standard Gaussian. So it's less clear what our guess for the limiting measure of L should be. Okay? And the way I like to think about the difference between these models, in this first model, the expected number of non-zero entries is going to infinity. And in the second model, the expected number of non-zero entries is going to some constant. So I should definitely mention, I'm using Gaussians here just to streamline the presentation. Every result, including this one and this one, they generalize at least a little bit, but usually quite a bit, okay? So any questions about these sparse models before I move on to the results? Okay. So these are the results that will hopefully be on the archive very soon, very, very soon. For the AN as above, with NPN going to some constant lambda, with probability 1, the empirical spectral measure of ln over square root of lambda is going to converge weakly to some deterministic limit that I'm going to denote by mu sub lambda. Okay. And then the result, that's the title of the talk. Now that we have these deterministic limits, we get that the empirical spectral measure of mu lambda, these deterministic measures mu lambda converge weakly to the free convolution of the semicircle and the Gaussian as lambda goes to infinity. So the way I like to think about what these results are kind of saying is the previous work said that if we let lambda equal NPN, okay, it's just the expected number of entries in a row. Then if you took the limit of lambda going to infinity with n, you get the free convolution. This is the known work. And oh, sorry, I went one forward. And these two results together basically say you can break this limit up in the only natural way. You can take the limit in lambda after taking the limit in n. And you still get the free convolution. That's going to be the last 10 minutes of my talk. Yeah. No, that's a really good question, and I'll explain why I think it's a difficult question.
So you got a little bit.
So you could probably get moments for AN. For LN, or for, mu lambda, or for, sorry, LN, it's a little less clear because you have like this diagonal in the adjacency matrix. So if AN was like literally the adjacency matrix of the graph, yeah. So we don't use a moment method. So possibly that could work. Really, I should definitely mention, this is one specific case of a more general model. So you don't have to have Gaussians. You can have, in the sparse case, you can have basically any random variable. It doesn't have to even have, it only has to have an epsilon moment, and we could still get convergence to some measure. And it's definitely going to depend on what random variable you have there. But you can even look at a non-sparse model where the entries of your matrix, the first absolute moment is infinite. So this very heavy-tailed model. So that's why we didn't take a moment approach, is it wouldn't work for most of the matrices we're looking at. This is just one special case related to free probability. And then for this result, you don't need Gaussians, you just need mean 0, variance 1, and then we use 3 finite moments. Okay. So how do you prove something like this? Well, we have to characterize these measures somehow. And we can get this through the Stieltjes transform. So this is just the negative of the Cauchy transform. We've seen this throughout the week. And then our characterization is going to look a little strange at first if you haven't looked at these very sparse or heavy-tailed models. But for Z in the upper half plane, for every Z in the upper half plane, we have that the Stieltjes transform of mu lambda is equal to the expected value of a random Stieltjes transform. So the Stieltjes transform of a random probability measure. And moreover, the distribution of this R lambda on the space of Stieltjes transforms is the unique solution to the following recursive distributional equation. I'll explain what I mean by that in a second, but let's just look at the pieces. So we have this N, which is just a Poisson of mean lambda. The Yj's are independent Gaussians, and the Rj's are independent copies of R lambda. And then these collections are all mutually independent of each other. Okay. So what is the recursive distributional equation? Well, the distributional equation is easy. You build a random variable according to the rules on the right. It's equal in distribution to the random variable on the left. Okay. In what sense is this recursive? The way you want to think about it is that these Poissons and these Gaussians, this is just part of some transform that takes a distribution on Stieltjes transforms to a distribution on Stieltjes transforms. So you feed in copies of a random Stieltjes transform and you get another random Stieltjes transform. And then the unique fixed point, and that's the distribution of R lambda. Yeah. Right, so this is Gaussian with sparse. Well, if you looked at a different model, yeah, so the Yj's are going to match whatever you're putting in as your sort of non-zero random variables. And then if you look at the heavy-tailed models, it'll change, but it'll always look very similar. It'll always look like a sum and another sum. Basically, all that's going to change is the Yj's and the N's. And then you wouldn't want to scale by lambda in that case. So how do you use something like this to prove our limiting result? Well, we need to characterize the Stieltjes transform of the free convolution. So this is not something we did, this was known. It turns out it's the unique solution of the following just regular recursive equation. So the Stieltjes transform is equal to the expected value of 1 over a Gaussian minus Z minus the Stieltjes transform. And this is for every Z in the upper half plane with the right asymptotics. So the right Laurent expansion at infinity. So I believe this follows from work of Bien in the 90s. That's what everyone cites, but I couldn't find it explicitly stated in the paper they were citing. Okay, so we know we have a unique solution to a recursive equation we're looking for, and the Stieltjes transform we have can be written as the expected value over some different random variables. So after passing to some subsequences, some subsequential limits, some details we're not going to talk about today. Really, in some sense, all we have to show is that as lambda goes to infinity, kind of these two recursive structures are the same. Okay. So this is kind of a sketch of the proof. So how do you see they're the same? You use some colors to make your life a little easier. So why is this red piece going to be converging to the Gaussian? This is actually kind of easy. So n is a Poisson, but it's of mean lambda. So for very large lambda, we're summing up essentially lambda random variables of mean 0, variance 1, scaling by 1 over square root of lambda. Central limit theorem tells us that's converging to a Gaussian. Okay. This you could do with, you could give to a first semester grad probability class who's learned characteristic functions. This blue piece is a little more complicated, but it's going to be another theorem we know super well at the end. So this denominator is the first piece we're going to deal with. So we have these RJs, they're still just transforms, so they're bounded for fixed J or J above some imaginary part. And then the YJs are Gaussians. So if we're summing up lambda of them, with high probability, the largest is square root of 2 log lambda. That's nothing compared to square root of lambda. So you justify sort of ignoring this denominator. Okay. So then you're really just summing up, essentially lambda random variables, scaling by 1 over lambda. All we care about is the expected value, but the expected value is just the expected value of Rj, which is the expected value of R lambda, which is S lambda. So the law of large numbers tells us that this is converging, or should converge to its expected value. We pass to a subsequence, so the expected value converges. So along these subsequential limits, we get the expected value equals expected value of 1 over C plus a Gaussian plus expected value. But then if you move the negative inside, and negative of a Gaussian is a Gaussian, and you're done. Any questions on this, on how to use this RDE?
So this is how we recover the time.
So
that kind of leads to the next question.
that Jorge asked earlier. We've seen now how this RDE can give insights into this, the limit as lambda goes to infinity of these measures. But a natural question is, what about finite lambda? So for every lambda in 0 to infinity, mu sub an over square root of lambda converges, and mu sub negative dn over square root of lambda. So they both almost surely converge to some weak, some deterministic limits. And then the question of the rest of the talk is that mu lambda? Is it the free convolution of these two respective limits? So I don't have an answer either way yet. That's something I was hoping to get a little bit more information on how to tackle something like this. My conjecture would be no. The way you kind of want to think about, or the way that's kind of helpful for thinking about it, is that in this, I guess in some sense, what was shown before is that in the large n limit for just like, GOE matrices, the diagonal and the GOE are kind of asymptotically free. I don't think you could expect anything like that for this very sparse model, because, the diagonal entry, because we're so sparse, like if lambda equals 1, the diagonal entry is basically just the largest entry in that corresponding row. It's just the only non-zero entry in that corresponding row. So these are going to be extremely dependent on each other. The AN and the DN are going to be extremely dependent on each other, even as the size of the matrix goes to infinity. Okay. But again, I don't have a proof that says it's not either. So if we're, probably explain something. If we're going to ask a question about this free convolution, we should probably get a sense of what we're taking the free convolution of. So Paul Jung has results from 2014. Again, this is one very special case, and it looks very similar, but now it's just for the AN, not the Laplacian. So if NPN goes to some lambda in 0 to infinity, mu sub AN over square root of lambda converges weakly to a deterministic limit. Moreover, the Stieltjes transform is the expected value of a random Stieltjes transform satisfying an RD. So again, this is one special case of a larger class of random matrices that Jung calls Levy-Khinchin matrices. I'll explain that name in a second. And basically, whenever you're looking at these very sparse or heavy-tailed models, you should always expect an RDE. Okay, it's either in the background or maybe someone used that RDE to prove something, and then you just see what they managed to prove with it. So for DN, we know quite a bit more. So for AN, all we really have is this RDE. And for DN, we know a lot more. It's going to converge to the probability measure of this random variable. So this is, again, just for the Gaussian case. And this is super nice. This is called a compound Poisson random variable, but it's just the Poisson sum of Gaussians. We know a ton about Poissons. We know a ton about Gaussians. So compared to this mu A lambda, we know a lot about this limit. Questions? Okay, next slide's the last, so we're going to get out of the conference on time. Okay, so given that our best description of mu A lambda is through an RDE, attempting to find a way to answer the big question led me to some other questions. So the first is, can the RDE describing mu A lambda be used to find an RDE describing this free convolution in the same way? So this would be perfect because I have an RDE for mu lambda. So if I had an RDE for the free convolution, I could try to compare some solutions. That might be difficult in practice because you're talking about like infimums over couplings of solutions and some kind of metric, but at least it would be, clear what you should do next. And the issue is that if we go back, let's look at the RDE for a second. So it's a property of Stieltjes transforms, so just think Cauchy transforms. We could try to use maybe some subordination functions to try and say something, but the problem is this is only distributional. We could put everything on the same probability space to get an almost sure equality, but then for every sort of realization, so every omega in the probability space, these functions only equal each other in distribution. For a fixed omega, they might be the Cauchy transforms or Stieltjes transforms of completely different measures. So there's no reason to think that for sort of a fixed realization, they look anything like each other or their subordination functions look anything like each other. So that was kind of one of the difficulties and why I wanted to learn more about subordination functions. If I don't understand the deterministic case, how am I going to do the random one? So that didn't really lead anywhere. So a more natural question might be, well, can we use these RDEs for Stieltjes transforms to describe the R transforms, right? Because R transforms work much nicer with free convolution. So that would be a better function to get a handle on. The problem is that this question is intentionally kind of vague because there's these deterministic measures that we have here, but they're kind of given by the expected value of some random measures. And do I mean the R transform of we want the R transforms of the deterministic ones, but because of the way the RDE is set up, it's kind of easier to get, some information about the random measures in the background. And then it's not clear, the next question, that is there any relationship between the expected values of R transforms of random measures and the R transforms of the expected measure, right? So if we had some nu that's random, they'll call it random. Could you say, even anything like this would probably be too much to hope for? That they're probably not going to be equal. This seems like a very nonlinear thing, but could you find some description of their difference maybe, or some other relationship between the two? And it's unclear to me. So I think I just want to conclude that, these questions are motivated by this Laplacian model, but because these recursive distributional equations show up in all of these heavy tails and sparse models, I think getting some answers to them could have, larger implications. So I don't want to get into this too much, but there's nothing like the connection between, GUE and Genebre and semicircle and circular operators. There's nothing like that for even heavy-tailed models, okay? Or it's not known. So these could be sort of a start towards that direction. All right, so we're gonna leave 5 minutes for questions, and thanks for listening.
Was you learn that one of the distribution of entities?
Yes. Yeah, because of this, or and the level of the RDEs, it appears so because we can't say much for any particular case. Like, oh, so this n is not the size of the matrix. This is a Poisson random variable.
Ah, that's
Yeah. So what you could do is you could try to compute the expected value at like even just like z equals I or something. And if you can show it's different for say Gaussians here versus sine Bernoullis, then that would imply they're different. But on the level of RDEs, they look very different. Yeah. But you would have to actually show them. Other questions?
What happens if we consider the input lambda tends to 0?
So if you got rid of this lambda scaling here, it's pretty easy to show. So I excluded lambda so I could scale by it here for this result, but you don't need that for convergence, right? This is just a constant. So it's just a change of variables. So if you got rid of that and then you looked at the RDE, where is it? So in that case, you would be thinking that you get rid of this lambda, and this one. And then this is a Poisson whose expected value is going to 0. It's pretty easy to show that it just collapses to a point mass. Okay, or it should. Yeah. Other questions? I think. Or, okay.
Good question about whether you have maybe I'm naive here, but do you have? Can you compute for future these zero dimension Cauchy transform?
At infinity. So probably the problem is that we have sort of this recursive expansion. So you can maybe try to expand this out by thinking of it as like a geometric series, and then you would get I guess you get 1 over z here. Yeah, you could try that. It's unclear to me. Yeah, so the issue is that for the sparse case, it could possibly work. For the heavy tail case, it's not going to work at all because we want to take expected values, and the expected value of this sum over yj's is not going to be finite. Yeah, it's only finite like when it's in this denominator. If you tried to do that, you're trying to. There's some cancellation going on that the expected value would lose. Yeah.
When then you said removing those that notation is something on. That will make the sparse representation, you know, the sparse
which model?
Sparse Erdos ranging model. It's like a random
even for NP going to a deterministic limit? Okay. Yeah, so I think that's another thing. That if A was literally the adjacency matrix of graph, I think that's where you have the most hope of doing anything. Then the YJs are just 1, and there's a lot more you could try. But again, in generality, we don't have much at all. Yes.
I think all of them have 2 methods. Not Laplacian, but we got a moment method and
right.
Digits.
Right.
And I think Jiang, he has the moment for Laplacian for large P.
Yeah.
So the way to get the moment for Laplacian at finite lambda.
Right. So for the sparse case, possibly there's the issue. The issue is that you don't like have your scaling is finite, and so things
matter.
Yeah.
It's not about the integers only come in terms of the number, but
right
now everything has individual can do that.
Yeah.
Another thing is for if I have a Gaussian with part Bernoulli with Panama or that, like just the A, you can do the second moment. I think we should definitely have a figure on that. And also for the long end. So it will be interesting to look at the spectral norm of Laplacian for finite now.
Yeah. Yeah, so that's another thing.
You expect for the long end.
It's unclear to me. I think you would expect an unbounded behavior even for Gaussian because of the Poisson nature. Yeah. Yeah, so I thought about that. I tried to do it on the level of Silch's transforms by trying to find a Z or trying to show every Z is, close to the support. But it was intractable. I couldn't get anything to work out. Yeah, there's a lot of open questions because RDEs are, so this RDE might be slightly easier to work with, but because it doesn't have that denominator term, but yeah. They're really hard to work with and say anything rigorous, at least in my experience. Or
Mu lambdas are absolutely confused.
Okay, that's a really great question. because I didn't, because I needed some tightness for random analytic functions in the upper half plane, you would want to do the same exact proof, right? You would want to pass to a subsequence. Basically what I could get is you could get that as lambda, 1 approaches lambda 2 or whatever, you could couple like the yj's, yjn, and then the limiting yj's and the Poisson and the limiting Poisson, you could couple them in a way to converge almost surely on the right probability space. So the only issue is that you would need that the subsequential limit of these distributions is a probability measure so that you have random analytic functions here. But maybe now that I know about the talk from earlier, I could map the half plane to the disk, check there, and come back, see if they're tight. Because if we had tightness of the subsequence of RJs for the random case, for the deterministic case up here, it's a lot easier. But for the random case, if we had tightness, I think it would be possible in full generality, not just the Gaussian with lambdas. Yeah, so it's a good question, but I didn't have a way to do that until possibly earlier today. Yeah.
So in your model, you take sparse Gaussians and you say something that you can take any other variable you want. That's true. So for instance, you can take a semicircular and you will get at the end a semicircular plus semicircular or something like that, or
you would get a Poisson sum of semicirculars. Yeah, which it's unclear what that is, right? So the reason you can take anything you want is, I forgot to mention why Jung calls these Levi-Kinchin. The D will always be the limiting probability, it'll be the probability measure of an infinitely divisible random variable. And so in the sparse case, it's always just a compound Poisson random variable. So that's why you can put anything you want in. But in general, it could be alpha stable. For his results, he can go fully general and include Gaussians, but we can't handle Gaussians. They have to be purely non-Gaussian for us. Yeah.
Other question? Start